Welcome, wonderful people. This is Mr. Ndabezita once again, and this time we are looking at precipitation, reactions, and solubility rules. These are one of the most important chapters in chemistry that one has to internalize. So let's see what really precipitation is all about. So they say to us that precipitation reactions is one in which dissolved substances react to form one or more solid products. So there is a reaction inside of whatever that is, but they dissolve and they react inside of a substance and they form a solid product. That's a precipitation reaction. A solid product is formed whenever the reactants react or they dissolve inside of a substance. That substance can be a liquid or whatever, and they form a solid product. And this solid product is what we call a precipitate. But let's continue and not conclude. Many reactions of this type are involved. Many reactions of this type involve the exchange of ions between ionic compounds in an aqueous solution and are sometimes referred as the double displacement, double replacement, or the metathesis reaction. So there is an exchange of ions whenever they react, whenever they dissolve inside of another substance. They exchange ions, and sometimes these ionic compounds in an aqueous, a liquid solution, are sometimes referred, this reaction is sometimes referred as the double displacement, double replacement, or metathesis reactions. Okay, that is fine. So second thing that we have to learn here is that when these reactants dissolve inside of an aqueous, a liquid substance, they dissolve into their ions based on the group in which they belong to. And this type of a reaction, sometimes a double displacement can take place, double replacement can happen, or metathesis reactions are also possible. These reactions are common in nature and are responsible for the formation of coral reefs in ocean waters and kidney stones in animals. So they are very, very important that we study them. They are used widely in the industry for the production of a number of commodity and specialty chemicals. So they are very much active in the chemical industry. The precipitation reactions also play a central role in many chemical analysis techniques, including spot tests used to identify metal ions and gravimetric methods for determining the composition of matter. Okay, the extent to which a substance may be dissolved in water or any solvent is quantitatively expressed as its solubility. So the extent to which a substance may be dissolved in water or any solvent is quantitatively expressed as its solubility, defined as the maximum concentration of a substance that can be achieved under specified conditions. So this is based on whether a substance can dissolve inside of an aqueous solution, and if that is possible, what is the maximum concentration through which this can take place. Right, that is fine. I think we understand that, but examples are always there to give us more explanation in these. Substances with a relatively large solubility are said to be soluble. So substances with relatively large solubilities are said to be soluble. So they are able to dissolve inside of an aqueous solution if they have relatively large solubility. So substances with a relatively large solubility tend to be soluble. They tend to dissolve inside of an aqueous solution. A substance will precipitate when solution conditions are such that its concentration exceeds its solubility. So when the concentration of a precipitate exceeds the concentration of its solubility, therefore it will not dissolve. A substance will precipitate when solution conditions, so this solution, whatever that it needs to dissolve inside, which we call a solution, if the conditions of that are in such that the concentration exceeds its solubility. So if the concentration of a solution exceeds the concentration level of a solute, this is a substance that needs to dissolve inside of a solution, therefore it will form a precipitate. It will not dissolve. Did we read that correct? A substance will precipitate when solution conditions, so meaning the conditions of that substance in which it has to dissolve inside, if the conditions of the solution are in such a way that when the solution conditions are such that its concentration exceeds its solubility. So when the concentration of the solution exceeds the concentration of the solute or of this substance that has to dissolve inside of it, therefore it will not dissolve, it will form a precipitate. Okay, substances with relatively low solubilities are said to be insoluble. So when a substance that is to dissolve inside of a solution has a low solubility, therefore it will be insoluble, because if its solubility is low and the concentration or the solubility condition of the solution is high, therefore it will not dissolve, it will form a precipitate. So in other words, when a substance has a relatively low solubility, it will be insoluble when it finds itself inside the concentration of a solution which is high. So if the concentration of the solution, the substance in which one substance needs to dissolve inside of, if its concentration is high and the concentration of a substance which we want to dissolve inside of it is low, therefore it will form a precipitate. So meaning substances whose concentration is higher than the concentration of the solution, if it is in that state, therefore they will dissolve. If the concentration of a solute is greater than the concentration of the solvent, therefore it will dissolve. If the concentration of the solute is less than the concentration of the solvent, therefore it will not dissolve, it will form a precipitate. Alright, that is fine. Let's continue in this. More information on these important concepts is provided in a later chapter on solutions. We will look into that, and we will also go and look at the gravimetric methods of determining the composition of matter. We will deal with that. For purposes of predicting, information on these important concepts is provided in a later chapter on solutions. Okay, that is fine. For purpose of predicting the identities of solids formed by precipitation reactions, one may simply refer to a pattern of solubility table that we will deal with in the next slide. Right, so here we are in the next slide, and we are provided with a table. And I want us to look at this table very carefully then. Soluble ionic compounds. Right, remember these are ions because they have either lost or gained electrons. We call them ions, but we have cations and anions. Right, so you are a cation if you are positively charged. You are an anion if you are negatively charged. And what do we know about those two? You are a cation if you have lost the electrons, therefore you are positively charged based on the periodic table, whether you are in group 1 or group 2 or group 3. And you are an anion if you have accepted an electron. So you are more electronegative, you tend to pull the electron to yourself. And when we dealt with net ionic equations, I explained that non-metals, in fact we looked into that, we saw that metals tend to give the electrons whenever they react, and we dealt with many things in there. So here we have soluble ionic compounds. So they are able to dissolve inside of another substance, or they are able to dissolve inside of a solution or a solvent. Remember what we said. We said the concentrations of these exceeds the concentration of the substance in which they dissolve inside. Therefore, they are going to react. They will not form precipitates. But if their concentration, the concentrations of these is less than the concentration of the substance that they need to dissolve inside, they will not react. They will form a precipitate. They will not dissolve, in other words. Very good. So we have them. These ones are soluble. They are able to react whenever they find themselves in lower concentrations of a solvent. Remember, a solvent, a solute dissolves inside of a solvent, and a solvent is a substance in which a solute dissolves inside of. Aye, Professor Maken. Continue. Right, let us look into this. So we have Cl minus, Br minus, and I minus. And they are able to dissolve whenever they, for example, reacting with Ag plus, Ag, Hg, 2 plus, and Pb 2 plus, and so on. Even F minus with compounds with group 2 metals, cations, Pb2 plus and Fe3 plus. That's fine. And then in here we have contain these ions, NH4 plus. Are there any exceptions in these? None. So these ones, they are soluble. They are able to react inside of a solution. And then we have them. Are there any exceptions? No, we don't have any exceptions in there. And these are the tables that we need to know and understand, because when we solve the problems, we will need to come to this table. Right, let's continue in this. And when we are here, we have those ones that now are insoluble. Their concentration is lower than the concentration in which they need to dissolve inside. Therefore, they will not dissolve. They will form precipitates. And these are the compounds that the cations and the anions that we have. You can just take a look at them, but I'm going to deal with this when we deal with the problems. I'll be reminding you many times of this table. Right, for the very first time we have some problems here. A vivid example of precipitation is observed when solutions of potassium iodide and lead nitrate are mixed, resulting in the formation of a solid lead iodide. Okay, This observation, the reaction in here is consistent with the solubility guidelines. So we will look at that reaction from the beginning and look at our solubility table guidelines and see what would happen in here. The only insoluble compound among all those involved in lead iodide, one of the exceptions to the general solubility of iodide salts is this. So the only insoluble compound among all those involved is lead iodide. So lead iodide is insoluble. And what does that tells us? The concentration, in other words, if they say the only insoluble compound among all of those involved is lead iodide, so the concentration of lead iodide is less than the concentration of the solvent where it needs to be dissolved inside of, and as a result of that, it will not form any cations. It will form a solid. So this solid, it's what we call a precipitate. Remember, in a precipitation reaction, a solid is formed. It is a product. Very important. So let us look into this reaction and see exactly what comes out of this. All right, wonderful people, let's continue in this. So we said a vivid example of precipitation is observed when solutions of potassium iodide. Okay, so potassium iodide. Right, let me check something. Let's go to the periodic table and look at potassium. It is in group 1. Very good. And iodine, let's look at iodine. It's in group 17. So the ratio of electron to electron is 1:1. So therefore we are correct to say potassium iodide will be like this. And remember, it's in an aqueous state. Why? Because they said the following. A vivid example of precipitation is observed when solutions of potassium iodide, so this is a solution, a solute plus a solvent result in a solution. So they are in an aqueous state because they dissolve inside of a solvent. Right, so this would be potassium iodide. Very good. Plus, let's go and check something else. And lead nitrate are mixed. Lead nitrate. So let's check lead. Lead nitrate. Let me check lead. PB. There it is. Let me just zoom in. Lead, there it is. It is in group 14. Therefore, it has a valency of 4. Lead Pb, lead nitrate. So you will have your lead Pb, lead nitrate. So this would be NO3. We know that this would be NO3. And what do we know about NO3? What do we know about that? Let me take you back here. So NO3 always result in, let me show you on the table here, NO3, where is it? Let me check here. It's not in here. It has to be, yes, NO3 minus. It's always a minus. So let's check in here. If I have a PB and it is in group 14, therefore how many NO3s will I need? I will need 2 of them. Very, very important. So this is lead nitrate. but this is in group 14 with a valency of 4. You will need 2 of these. And remember, this is not a balanced chemical equation. You will see why I say you need 2, why we are not writing 4 in here. You will see that. Right, so this is also in an aqueous. Remember, they dissolve inside of a solution. Sorry. Very good. So when potassium iodide reacts with lead nitrate, what is it that we get? Let's go and check. Let me go back. So potassium iodide and lead nitrate are mixed, resulting in the formation of a solid lead iodide. Solid lead iodide. I forgot the volume. Solid lead iodide. So PbI. Solid lead iodide. Right, how many of these do I have? This has a valency of 4. This has a valency of accepting 1. So how many of this will I need? 2 of them. And you will see why. And remember, this is a precipitate because it forms a solid. Plus, this is not the only product we can get from this. This reacts with this to form lead iodide. And let's check this. Let's verify why we have this solid. Remember, these are the exceptions. Let's go and check this lead iodide, lead and iodine. Let's check whether this will be a precipitate. So you have lead, there it is, sorry, you have lead and iodine, and these are the exceptions. Yes, chlorine is soluble, but with the exception of Ag, Hg2 2+, and Pb2+. Also an exception with Pb, there it is. It is an exception with lead. So when chlorine reacts with lead in a precipitate, a solid will be formed because the concentration is lower than the concentration in which it finds itself in. Therefore, it will form a precipitate, a solid. That's why we have it in here. Very, very important that we understand what the table really means. These are the exceptions. Yes, chlorine, bromine, iodine, and fluorine, they are soluble, but these are the exceptions. These are all the exceptions. It is an exception with group 2 metal cations. So very, very important that we note the exceptions there. So because chlorine is an exception with lead, therefore this will form a precipitate. Very, very important that we understand this. So the other product that might come from here, if lead forms a precipitate with iodine, the other one left is potassium nitrate. So I'm going to say KNO3. Let me do this. KNO3. The question is, how many NO3s do I need? And remember, this is in aqueous because this does not form a precipitate. This one. Right, let's check why am I not saying in bracket and writing 2. Potassium is in group 1. Let's look into this. It is in group 1 with a valency of 1. And what else do I know? Sorry. What else do I know? NO3 accepts A1. NO3 accepts A1. Therefore, I don't need 2 of this because it's K plus and NO3 minus. So everything is fine. Now the question is, let's write a balanced chemical equation, ionic equation for this, and the net ionic equation so that we can end up with this. Very, very important. Let's go and try to do that because we have learned that in the previous tutorial where I dealt with net ionic equations. So let's go and try to do this. So the first thing that we will do, we will write a balanced chemical equation. Very good. So that is the very first thing that I will do. So let me just copy all this, copy this and paste. So let me balance. Let's start with K. K is 1, K is 1, K is balanced. Iodine 1, I 2, so I need to put a 2 here. But by doing so, I will need to put a 2 there for K. And when I do that, I have 2K, 2K, 2I, 2I, this side is fine. I have 1 PB, 1 PB, I have 2 of NO3, I have 2 of NO3. So it is very much balanced. Right, so now I want to write an ionic equation or reaction. So I'm going to copy a balanced one. Remember, we need to do this from a balanced chemical equation and then write an ionic one. So what I'm going to do there, I'm going to say 2K. Remember, it has a valency of 1. So I'm going to say plus 1, but I know how many I have, 2 of them. And remember, they are in an aqueous state. Very important. And then I have 2I, so 2I minus 1. Very, very important. It's also in an aqueous state. Plus, I'm done with this. Now I am here. PB to an exponent. Please be very, very careful. PB, even though it's in group 4, we use the table. Look what is happening here. Even though it's in group 4, but we use the table to help us. What is PB? It's 2 plus. Very important. So I'm going to come in here and say 2 plus. Very important, because the coefficient is 1 then. And remember, it's in an aqueous state. Plus, and in here I'm going to bring this 2 to the front because I have 2 of these. We dealt with this, so I'm going to say NO3, and I'm going to raise this 2 minus 1. Remember this, we dealt with this and I explained exactly what is happening here. So just go and look at the lecture where I deal with ionic equations and you will understand exactly what is happening here. Very good. So from there, I'm fine. From this side, I've dealt with this, I've dealt with that. Now let me bring in the arrow. Remember, if you have this as a product, don't change, just take it as it is. We dealt with this, just paste in there. Plus, let's work on this. So I have 2K plus, so I might as well just copy this. Just copy this and just paste. Sorry, let me just paste. Plus, and I have 2NO3 minus. Very, very important. Don't forget 2NO3. So I might as well just copy this. Copy this and paste. And we are very much fine. That would be, let me get rid of this one then. Sorry. Let me get rid of this. And then from there, I'm going to write a net ionic equation. Right. So remember what we do. We look from the left, that which did not change as a reactant and also as a product. So I'm going to get rid of this, get rid of that. I'm going to leave this, I'm going to leave that, but I'm going to get rid of this and also of that. So what is left on this side? It's this copy this, paste, plus what else is left? This. So I'm going to copy this and I'm going to paste it. Very good. So remember what I have got rid of. Let me check. Oh, sorry, this one is out. I'm very sorry. I'm very sorry. This one is out because it doesn't change from this side and that side. So I'm left with this and that. So let me just copy this, copy this and paste. Very good. So those are the only ones left. I cancelled this one and this one. I'm left with this and this, so I can have my arrow. So I cancel this and this, and I'm only left with this. Copy this and paste. Very good. So we are very much fine. So that's how this equation became to be this. Now let's read this. This observation is consistent with the solubility guidelines. The only insoluble compound among all those involved is lead iodide, and we saw that because of the exception, one of the exceptions to the general solubility of iodide salts. So this is what we get. Lead iodide is a bright yellow solid that was formerly used as an at its pigment known as iodine yellow in figure 4.4. The properties of pure lead iodide crystal make them useful for fabrication of X-ray and gamma ray detectors. So they play a very important role. Right, let's continue in our reading. Let me just do this. The solubility guidelines in table 4.1 may be used to predict whether a precipitation reaction will occur when solutions of soluble ionic compounds are mixed together. And there's a lot of theory that is involved there. Now I'm going to come here. Predicting the precipitation reactions. Predict the result of mixing reasonably concentrated solutions of the following ionic compounds. If the precipitation is expected, write a balanced net ionic equation for the reaction. They say potassium sulfate and barium nitrate, lithium chloride and silver acetate, lead nitrate and ammonium carbonate. And we will be dealing with this in the next lecture. So please stay in tune with Papa Fanzo. Please like, share and subscribe, and I will see you in the next tutorial where we'll be dealing with predicting precipitation reactions.